Welcome to Lecture 21. In this lecture, we'll clue up talking about solenoids by doing some examples, and then we'll move on to talking about magnetic force. For this example, we have a solenoid which is 35 centimeters long, so our length is 0.350 meters. It contains 450 circular coils, so N equals 450. The diameter is 2 centimeters, that makes the radius 1 centimeter, 0.10 meters, and the current flowing through our solenoid is 1.75 amps, and we see the direction of that current flow in the picture. We're asked to find the magnetic field, so let's use our equation for finding the magnetic field at the center of a solenoid. B is equal to mu naught times N times I divided by the length of the solenoid. Mu naught is 4 pi times 10 to the minus 7 Teslas meters over amps. Multiply that by the number of coils, 450. 450 doesn't have any units. Multiply that by the current, 1.75 amps, and divide it by the length of the solenoid, 0.350 meters. If you do that, you get a magnitude of magnetic field, 2.83 times 10 to the minus 3 Teslas. Magnetic field is a vector, so we have to find the direction, and we'll use the right-hand rule to find the direction.
Let's try and sort out the direction of the magnetic field in our solenoid. So I'm going to use this slinky and say this is our solenoid. If you look at the picture shows that the current goes up in the back of the solenoid and comes down around in the front. So the current is coming this way. What you do is you take your fingers, you make a circle with your fingers, where the circle of your fingers matches the current direction. So I'm going to take my fingers and I'm going to curl them so they go up in the back and down in the front. I look at what my stuck-out thumb is doing. My stuck-out thumb is pointing this way. So that's the direction of the magnetic field in the center of our solenoid. We approximate it as ideal, so we say that the field outside the solenoid is 0.
So let's put on a Cartesian coordinate system. I'll take plus x to the right, plus y up, plus z out of the page. Our magnetic field was pointing this way. That's in the positive x direction, so our magnetic field vector gets an I hat. What we do now in part B is we take our slinky and we just stretch it until it's a long straight wire. So it's no longer a set of coils, now it's long and straight, so we've essentially uncoiled it. Let's say that our current is still coming in from the right side and flowing towards the left side. So there's our current I. And now we're asked to find the magnetic field at 1 centimeter from the wire center. So a distance r equals 1 centimeter, 0.10 meters. Let's use our equation for magnetic field around a long straight wire. B is equal to mu naught times I over 2 pi r. This is familiar because we've done this in earlier lectures. So 4 pi times 10 to the minus 7 Teslas meters over amps times the same current, 1.75 amps, divided by 2 pi times the distance from the wire, which is 0.10 meters. Put that through the calculator, we get 3.5 times 10 to the minus 5 Teslas. This is considerably smaller than what we had for the solenoid. And the reason it's smaller is that it's just a completely different geometry. A long straight wire is not a solenoid, so of course it doesn't have the same magnetic field. If you wanted to put in your direction, you would remember that the magnetic field makes big circles around the wire. To get the direction of your magnetic field, you use your right-hand rule, so you put your fingers in the direction of current. So you put your thumb in the direction of current, so your thumb points towards the left. Your curled fingers show the direction of the magnetic field. So your B goes down in the back, goes up in the front. So at point P where we found the field, it's coming straight towards us. That makes that in the plus K direction. So if we wanted to write our magnetic field as a vector, we would add a K hat. In this example for Ampere's law, we're going to find the magnetic field of a toroidal solenoid. So a solenoid is just like our slinky. To make the toroid, we take our slinky and we just loop it around so it connects. So this is what a toroidal solenoid is going to look like. In our image, we're going to say that the current goes in through the middle and loops around out from the back. So it's coming towards you at the top, going away from you at the bottom. In our picture then, as we draw the current, we're going to say it goes in on the bottom, comes out at the top. We'll represent the current that way. We're going to apply Ampere's law now and try and figure out the magnetic field in all the places. So let's start to establish our picture of what's going on. The current goes away from us in the center, so I'll draw X's all around the center, comes towards us around the outer perimeter. So I'll draw a picture like this going all around the loop and end up with a picture that looks like this. So I drew this kind of not live just so it wouldn't take forever. Let's think now about the magnetic field and how we're going to choose our paths. Let's think about one loop of our wire. The current comes out of the page right here and it goes into the page right here. So this is a loop of current. If you use your right-hand rule, you can see that the direction of the magnetic field right here will be in this direction, and that's a problem we worked through earlier. If you come around to another spot, the magnetic field comes out, the current comes out there and in here. So for this particular loop, the magnetic field points this way. That tells us that the magnetic field is always coming around this way. The magnetic field makes a circle. Okay, so what we're going to do about that is when we pick our path for Ampere's law, we're going to use a circular path. We're going to choose 3 spots for our path. We're going to do one path right in the very center. So there's path 1. We're going to do one path in between the coils. My circles aren't perfect. If you want a really nice picture, they are in your textbook. So there's path 2. And then for path 3, we're going to go outside altogether. Once we've covered all 3 of those areas, that will give us the magnetic field in every spot. So for each of those places, we're going to be applying Ampere's law that says the integral of B dot ds is equal to mu naught times I. I stands for the current inside that closed path. ds is our part of our closed path. So let's start with path 1. We'll choose a path in the middle where there's no solenoid at all. We'll bring our path around this way. So this is for path 1. We'll write Ampere's law. The integral of B dot ds equals mu naught times the amount of current inside our closed path. The amount of current inside our closed path is 0 because remember our wires are coming this way. So this is where our wires are. There are no wires inside that closed path, so there's no current inside that closed path. This tells us that the magnetic field in that empty space is equal to 0. Okay, there's path 1. Let's do path 3 next. And I picked to do path 3 next because it's also pretty easy. So for path 3, I'm going to take my closed path outside of everything. So there's path 3. I'll come around this way on path 3. We'll write Ampere's law again. The integral of B dot ds equals mu naught times the amount of current inside. Now this time we do have wires inside of our path. That's definitely true. But look at each set of wires. For every loop that has current out of the page, there's current into the page. So the number of loops that have current flowing towards you is equal to the number of loops where current flows away from you. That means that the net current within that circular path number 3 is equal to 0. So our result is that the magnetic field is 0 when we're outside the toroid as well. So therefore, all of the field is inside the loops, or the windings of the solenoid. So all of the field is inside that solenoid itself. So we'll look at path 2 next. Let's draw our path 2. So that's a circle that comes around within the windings. It's not the best circle I've ever drawn, but hopefully you get the idea. It is supposed to be a circle. So here's path 2. We'll write Ampere's law. The integral of B dot ds around our closed path is equal to mu naught times the amount of current inside our closed path. So for this time, all of the current inside the path are all represented by all those x's inside the circle. So that's the amount of current that's inside. The dots inside the circle, they're outside the path, so they don't count. Let's deal with our two sides of our equation now. The integral of B dot ds. We already established that the direction of our magnetic field was parallel to the direction of that path. So we've got the integral of B times ds, magnitude of B times the magnitude of ds, where ds is a small segment of our path, times the cosine of 0. Those two things are parallel, so the angle between them is 0. So we've got the integral of B times ds. We're a constant distance away from the wires at every time, so the B is going to be constant. We're left with the integral B times the integral of ds. What we get when we integrate ds is the entire path length, so that's B times 2 pi r. Okay, now I'm going to put my r on my picture here. Okay, so that's that side of the integral. What about the other side, I enclosed? So the amount of current inside, every single little loop here, every single x represents current I flowing into the page away from us. We have n of those little loops, so the total amount of current is n times I. That's how much current overall is enclosed. Okay, so for the left-hand side of the equation, we'll fill in B times 2 pi r. For the right-hand side, we'll fill in mu naught times the total current, which is n times I. That gives us B is equal to mu naught times n I over 2 pi r. Okay, this slide is a tiny bit full. I'm just going to spill on to the next slide while we discuss that result. B equals mu naught times n I over 2 pi r. Well, let's look at this. Let's remember that we're dealing with a solenoid, and let's ask, what is 2 pi r? 2 pi r is the circumference of the circle that goes around the inside of that solenoid. So this is equal to the length. That means n over length is what we called coil density in our solenoid. So the magnetic field of our toroid is exactly the same as the magnetic field of a solenoid. So I guess that's a pretty good result. Since a toroid is a solenoid, we've just bent it into a circle.